So as I was saying last time, we were halfway through Chapter 10, Section 2, and we were talking about some guidelines for accounting, and these are going to be really important as we move through the chapter. In fact, whenever we get to a accounting problem, if we get to a problem that says how many, which most problems do in this chapter, this is the way we're going to have to think. And so here's what we put up at the end of class one time. We have two questions that we want to ask if the question says how many. Question number one is repetition allowed? And of course that can only be answered yes or no. If the answer is yes, then we're going to draw blanks and use the fundamental counting principle. Now, we'll use the fundamental counting principle if it meets the uniformity criterion. If it violates the uniformity criterion, then we'll have to back up and do a tree diagram. Okay? But most of the time we'll be able to draw blanks. Now, if the answer to is repetition allowed no, then we have a second question to ask. And that second question was, does order matter? Which again can only be answered one of two ways. Either order matters or it doesn't. If it does, then we're going to use a permutation. Now leave a little room off to the side of the word permutation there, and we're going to give you a little bit of a hint about if you're having trouble figuring out when order matters and when it doesn't. We're going to have a few clue words, and we'll put those over there. And if order doesn't matter, then we'll use a combination, both of which we talked about at our last meeting. Okay, so sometimes the hardest part for a lot of students is that second question, figuring out if order matters or not. What I've been encouraging you to do to try to figure that out is list down one possible way that the series of events can occur, and then switch a couple of them and see if you get something different or not. If you get something different, then order matters. If you don't get something different, then it doesn't matter. It's the same thing. However, sometimes students still get confused. So I'm going to give you now some key words that usually mean one or the other as far as permutation or combination. So if in your problem you see words like arrangements, schedule, and obviously order, then you probably have a permutation. Arrangement, schedule, and order. How many arrangements, how many schedules, how many orders? If you see the following words like group, how many groups? Sample, how many samples? Selections, Now those are the three the book gives. I'm going to give you a couple extra. Committees, or subsets. Usually the order does not matter. The order in which you choose the individuals does not matter in any of those. You don't get something different if you switch the order in which you choose the individuals. And so those are keywords for the combination. So if you're a person that has trouble with order, then those keywords might be really important to you. Okay, so last time we talked about how to find a permutation and a combination on our calculator, but we didn't really look at very many counting problems where we had to apply those. So let's look at several now. And to help us on our journey, we are going to begin with example number 4. Example 4 says, suppose certain account numbers are to consider. I don't want that one. Dadgummit. That didn't say what I thought it was going to say. So I changed my mind. Let's start with example 8. I'm on page 548. Which says a common form of poker involves hands of 5 cards dealt from a standard deck consisting of 52 cards. How many different 5-card hands are possible? Okay, so we're getting ready after this chapter to do a chapter on probability. And when you get into a chapter on probability, you get lots of card problems, like a deck of cards. So sometimes in my classes, I've got students who haven't played cards at all. So let me just ask you, how many of you, hand up here, are very familiar with a normal 52-card deck of cards? I played a lot of cards in my life. Okay, those hands are half up, so I can't really tell. How many of you are not familiar with a normal deck of cards? Okay, we've got one. So let's talk through a deck of cards just for a moment here. So how many different 5-card hands are possible? Why am I getting a snowstorm all of a sudden? There we go. Okay, so the question is going to be posed first to Brandon and Katie. Well, not Katie, because she's just learning cards here a little bit. So we'll go Brandon and Chris. So if I deal you 5 cards out of a deck, is repetition allowed? No, I'm not going to deal you the same card twice. That's right, it is not allowed. So since repetition is not allowed, then we're not going to draw blanks. See, I'm working down my list here. So I'm going to go to the second question. It's no. So does order matter? No. Okay, talk me through how you know order does not matter, Brandon. You're correct, by the way. Okay, but what does it have to do with order? Let's put it this way. Let's look at this 2 different ways. If I dealt you the ace of hearts and the 5 of clubs, call that 5C, the 4 of diamonds, the 6 of clubs, and the king of spades, that'd be a hand. That'd be a set of 5 cards. Now, if I switch the order of any 2 of those, if I dealt you, instead of dealing you these cards in this order, if I dealt them to you in this order, 5 of clubs, then the ace of hearts, and then the 3 others in whatever order, are these 2 hands the same hands or not? 4 of diamonds, 6 of clubs, king of spades. Are those two the same hand? They are the same hand, aren't they? It doesn't matter what order you get the cards in, you have the same set of 5 cards. So therefore, order does not matter on this problem, and it means we're going to use a combination. The other hint that we have as to why that's a combination is the word set, which is similar to the word subset. Okay, so that kind of lets you know that we're using a combination. So a combination of, we're picking from 52 cards, and we're picking 5 of them. Okay, so go back to your calculator and make sure you remember how to do a combination of 52 things 5 at a time. Remember, you're going to hit the 52 in first. Then you're going to find the button that says, it probably looks like this, NCR, on most calculators. On a graphing calculator, that's in the math menu and then the probability submenu. Did you get a 52 combination 5 to be 2,598,960 different sets of 5 from a deck of 52? That's why no 2 game of cards is the same. Because when you deal 5 card hands, there are so many ways that they can happen, you hardly ever get the same hand twice. Okay, that's example 8, where we ended up with a combination. Example 7 is on the same page as example 8. I think we might have actually done this problem last time, not for sure. It says find the number of different subsets of size 2 in the set A, B, C, D. Okay. So subset just means how many ways can I pick 2 of these 4. That's what it amounts to. So because it's a how many question, we always go back to our guidelines, always. So if I get how many, the first question I'm going to ask is repetition allowed? Well, am I going to pick the same letter twice in my subset? Well, obviously not. Repetition's not allowed. And then the second question is, does order matter? Well, if I pick A then B, is that the same subset as B then A? And the answer is yes, it is. It's the same one because it didn't say how many different orders of 2 letters can I have. It just says how many subsets. So, since order doesn't matter, this is going to be a combination. Plus, as we said a moment ago, the word subset is a key word to let us know that we probably have a combination. So this is going to be a combination of 4 things, 2 at a time. And that should turn out to be 6 on your calculator. Example 3 is back on page 546. I'm going to read it and then I'm going to ask Tristan and Summer a question. How many non-repeating 3-digit numbers can be written using only the digits 3, 4, 5, 6, 7, and 8? Okay, well this question started with the words how many. So Tristan and Summer, my question to you is, what's the first question we're going to ask ourselves? Good. Is repetition allowed? And here the question says how many non-repeating 3-digit numbers. So repetition is not allowed, so we're not going to draw blanks. Okay, so I've got to ask if order matters. If we're not sure, then let's try a possibility. 3 345 would be one 3-digit number I could make without repeating digits. If I switch any two of those, do I get the same thing? Is 345 and 435 the same thing? I think last time we said no, it's obviously not. So since I got something different when I switch the order, then order does matter. Because when I switch it, I get something different. So this is a permutation. I'm picking from 5, and I'm picking 3. So if I go, you can't see, you can kind of see that. If I go 5, permutation 3, I get 60. Okay, so there's a permutation, there's a combination, actually two combinations. Now, so these next three problems, we're going to kind of mix them in together. So let's see which ones end up being permutations, combinations, or drawing blanks. That came through fuzzy. Ask that question again.
How did you get 5? I thought it was supposed to be 6 because there's 6 numbers.
You're right. There are 6 numbers. Thank you. So this is wrong. 1, 2, 3, 4, 5, 6. Yes, permutation is 6 things, 3 at a time. Thank you for catching that for me. So 6 permutation 3 is actually 120. Way to go, Mr. Black. Okay, so that's better. All right, the next thing I want to look at is example 10. But I don't think I want you guys to turn there. I don't think I do. I think I just want you to hear the problem, which I will read slowly, and I'll put it on the screen. But if you look there, it's gonna take all the thinking out of it for you because I got the answer right below it. Okay, so the question here says, in how many ways can a mother, probably hard to see, in how many ways can a mother distribute 3 different toys among her 7 children if a child may receive from anywhere from none to all 3 toys? Okay, so that's hard for you to see, so I'll just take it back off the screen, but let me talk through the problem one more time. So I've got 7 kids, and I got 3 toys, and the toys are all different. And we're going to give out the 3 toys, and any kid could get anywhere from 0 to all 3 of the toys. So in other words, I might give, say I got a Snickers bar, and a basketball, and a iPad that I'm giving out. I could give a Snickers bar to Brandon, give a basketball to Tristan, and then Brandon could end up with the iPad as well. So one kid could get anywhere from none to all 3 of the gifts. Okay, so let's ask the question. Is repetition allowed? So Katie and Robert, what do you think about that question? Is repetition allowed?
No.
Katie, what do you think about that?
No.
Okay, what is it in the problem that gives you guys the notion that repetition is not allowed?
3 toys are unique. There's only 1 of each.
That's true, but let's think about the question that I'm asking. I'm asking, how many ways can I distribute the 3 different toys among her 7 children? So I see why you're thinking the way you're thinking, but let me challenge your thinking a little bit. Think of it this way. There's 3 parts to this problem because I'm giving out 3 toys. Now when I say is repetition allowed, I'm thinking in terms of the kids for a moment. So don't think about the toys, think about the kids. So in other words, could Chris end up getting the first toy and the second toy?
Yes.
Yes, he could. So actually repetition is allowed because I could give a toy to the same kid more than once. And since repetition is allowed, then we do have to draw blanks. And so if I take the first gift, which was whatever I said, a Snickers bar, there's 7 different ways to give that one out. 7 different ways still to give out the second gift, because there's still 7 kids, and 7 different ways to give out the third gift. And if you take 7 times 7 times 7, or 7 to the third power, you're going to get 343. So these problems can play with your mind a little bit. You could see what Robert and Katie were thinking there, because you didn't have identical gifts. But you have to think about as far as the way the events can occur, and when we think about the way the events can occur, we're thinking about, can one of the kids get more than one gift? The answer to that was yes. Okay, let's go next to, once again, example 12 is on page 551, but again, I don't really want you to look at it for a minute. I just want you to hear it. Every member of the Alpha, Beta, Gamma fraternity would like to attend a special event this weekend, but only 10 members will be allowed to attend. How many ways could the lucky 10 be selected if there are a total of 48 members? Okay, so we got 48 members in this fraternity. 10 are going to be chosen to go to an event. Okay, let's take the entire class at Anna and ask them, is repetition allowed? Brandon, what do you think?
No.
What do you think, Chris?
No.
Okay, why do you guys think no?
Because the same member can't go twice.
That's right. We're not going to choose the same member for 2 slots. Okay. All right. Second question is, does order matter? Okay, so I'm not going to list it out this time. I want you guys to think through if the order that I picked those 10 members, if I change the order, does it give me a different set of 10 or not? So does order matter? Chris, what are you thinking on that one?
No.
You're correct. The order doesn't matter because it doesn't. If I picked Chris and then Robert and then 8 others, that's not anything different than if I picked Robert, then Chris, then 8 others. It's the same thing. So this is a combination of 48 things, 10 at a time. And if you punch that in on your calculator, you only get 6,540,715,896. That's all. Good thing we didn't have to try to sit and list all those out with a tree diagram. Okay, last problem I want to look at is example 13. And it also is on page 551. It reads like this. When the 10 men from example 12 arrive at the event, 4 of them are selected to escort 4 homecoming queen candidates. And how many ways can this selection be made? Okay, so the 10 guys are the pot we got to choose from, and they're going to escort 4 ladies. And the question is, how many ways can that occur? How many ways can that happen? So, let's see what we got shaken here this time. Is repetition allowed? Are we going to allow more than one guy to escort? I said that wrong. Are we going to allow the same guy to escort more than one lady? Are we going to allow repetition of fellas? And the answer is no. So we're not going to draw blanks. So the question then becomes, does order matter? Okay. Well, let's think about that. Here's lady 1, lady 2, lady 3, and lady 4. If I pick Bill, then David, then Fred, then Jim, is that the same selection? Are they paired up in the same way as if I pick David, then Bill, then Fred, then Jim? If I switch the order, do I get something different? And here I do get something different because we don't have the same thing with lady number 1 as far as who is escorting her. So in this case, order does matter, and we're choosing from a permutation, we're choosing from 10, and we're choosing 4. And that number ends up being 5,040. Now, that problem illustrates why it's important to be able to think through it like this, switching the order and seeing if you get a different result. Because if you read that question again, if we read it again, it says, in how many ways can this selection be made? Well, the word selection usually comes with a combination. But the reason that this did not end up being a combination is because they were escorting 4 females. If I would have just said, how many ways can I pick 4 guys, then the order wouldn't have mattered. But when we say they're going to escort 4 females, then all of a sudden the order does matter. So these problems play with your mind a little bit. They make you think. And they get easier with practice. So you just got to spend time on them and practice. And the ones you struggle with, come back and get help on, and then go back through them again. Okay, your assignment for page 553 is going to be the following. 1 through 10 is basically just calculator work. We're going to go 15. Well, first of all, let me ask you, I didn't give you an assignment off of this page last time, right? I did or I didn't? No. Okay. Okay. 15 through 28. 36 through 39. And 41. Okay, and that's a wrap on 10-3.